The reverse sprinkler is a physics brain teaser that was made popular by Richard Feynman. Take a garden sprinkler like this. I think we all have good intuition for which way it turns as fluid spurts out. But what happens if we reverse the flow and suck fluid into the sprinkler? Does it turn, and if so, which way? It's actually surprisingly complicated, and still attracts some robust debate at physics parties, at least the ones I go to. Recently, there was an impressive paper published on the topic by a group from NYU. What they show is that the internal flows into the hub are skewed, and those skewed internal jets are what drives the rotation of the sprinkler, by what they describe as a rocket-like mechanism. And this is where I'm going to throw a cat amongst the pigeons, because while I agree that these internal flows are key to the problem, what I see in my simulations is not really very rocket-like. So these are the 5 sprinkler designs I put through a simulation. I've uploaded all these designs in simulation control files so you can experiment with them yourself if you're that way inclined. First, let's start from B and C, where the arms are offset, so we don't have to worry too much about the skewness within the flows here. There's a definite forced asymmetry. For B, you might guess from the rocket-like model that it will rotate clockwise, and it does. But let's actually break down where the torque is acting. This is a cumulative torque plot, where I've integrated torques along the sprinkler up to a given point, from the end of the arm at the left of the plot to the center of the sprinkler at the right. So the value at the right axis is the torque from the whole bottom half of the sprinkler. And here it's negative, which means clockwise per the right-hand rule. But here's something super interesting. If we just look at the torque on the arm, the blue part, it's actually in the opposite direction. That's not very rocket-like. Where is the clockwise torque coming from? It's coming from the pressure gradients where the arm flow meets the circulating hub flow. Here you can see high pressure on this side and low pressure on this side, and that's what's driving the final net torque. And design C is precisely the opposite, as you might expect, with the graph going negative and then positive, and it rotates in the other direction. Again, the direction is consistent with the rocket model, but where the torques are acting is not. So let's come to design A, where there's no geometric asymmetry, and the flow skewness is going to play a part. When you have a flow going around a bend, you have an effect called Dean flow, where the flow after the bend is skewed to the outer side, and there's secondary flow in the perpendicular plane. What I found in my simulations is that the angular momentum flux from these two effects actually largely cancels, and when we look at the torque plot, the torque on the arms ends up close to 0. The dominant torque is again at the arm-hub interface, and it's coming from the pressure gradients where the arm flow meets the hub flow. Now, because this effect depends on the hub flow and what's happening in the hub at a given time, it's very fragile, and if we start getting turbulence in the hub, the torque starts bouncing all over the place. I can't guarantee this transient simulation is 100% accurate to reality, but it gives you an idea of why the reverse sprinkler is very temperamental in experiments. That's the short version. For more depth, you can have a look at my blog post.